I will give the third lecture of week 3, and in this lecture I will talk about two conventions which are used to describe the symmetries of crystals. Later on we will see that this convention is also used to classify crystals, but at this point I just want to introduce these two conventions which are referred to as the Schoenflies and the Hermann-Mauguin Conventions. These will be used just to describe the symmetry elements. So, let us look at these two conventions. So far we have seen the different point symmetry elements, and we remind ourselves that these point symmetry elements are common to both molecules, isolated molecules. That means if you just look at a molecule and you look at a symmetry of a molecule, you can it will have these point symmetry elements, and crystals which are essentially infinite array of atoms and of atoms, okay, which consists of infinitely many atoms. So, unlike molecules which just consists of a few atoms, crystals consist of infinitely many atoms, but they are arranged in a particular way. Okay. So, there are symmetry elements called point, we have seen these symmetry elements called point symmetry elements. Okay. What are the symmetry elements that we have seen? We have seen the point is a symmetry element, a point is the geometric point is a symmetry element, and that generates a symmetry operation called the center of inversion. So, a point can be a center of inversion. So, this process of inversion about the point is a symmetry operation. You can have a plane and the symmetry operation can be reflection about this plane. You can have a line which is a symmetry element, and the symmetry operation can be a rotation or a simple rotation or a proper rotation about this point. You can have a line, a symmetry element which can be an axis of roto reflection. So, a rotation followed by a reflections. This is also referred to as improper rotations, especially in molecular group theory. This is referred to as an improper reflection in molecular symmetry. You can also have roto inversions. Okay. So, this is a rotation followed by an inversion. Okay. So, these are the different symmetry elements and the various symmetries that we have. Okay. Now, there are two notations that are used, okay, and I will write them right here. So, the first is the notation for molecular group theory, which is due to a person called Schoenflies. Okay. And in the Schoenflies notation, the center of inversion is denoted by a letter I. So, if a molecule has an inversion symmetry, okay, you refer to by I, you refer to this operation of inversion about the center. Okay. So, the other notation which is actually very commonly used, which is more commonly used in crystallography, is the Hermann-Mauguin notation. Okay. And in this Hermann-Mauguin notation, the operation of inversion is referred to as a 1 bar. Okay. So, 1 bar refers to this operation of inversion. The next symmetry operation is reflection about a plane, and again this in molecules can have several axes of reflection. Okay. They need not have only one axis of reflection, several planes of reflection. So, now the notation used for these reflection operations, okay, so you typically use the symbol sigma to denote a reflection, okay, and in molecular symmetry there are different kinds of reflections. Okay, so you differentiate between the different kinds of reflections. Okay, so you might write sigma v or sigma d or sigma h. Okay, so these are different reflections. Okay, they are defined with respect to the molecule. Okay, so there is v d h stands for vertical, diagonal, and horizontal. Okay, I won't be discussing that in detail, but you will see symbols like sigma v, sigma d, and sigma h. You might have already seen these. Okay, when in other courses on molecular symmetry. Okay, so these are this is the notation for reflections, reflection symmetry operation. Reflections in the Hermann-Mauguin notation are simply shown by the letter M. M stands for a mirror. Okay, simply shown by just one letter M. Okay, now if there are multiple mirrors, okay, if there are multiple mirrors in a crystal, okay, multiple mirror planes in a crystal, then you can use MM or MMN and so on, MMM and so on. So you can use multiple M's if you have multiple mirror reflection symmetries. Okay. Now coming to rotations, the proper rotations in the molecular notation or the Schoenflies notation are denoted by C with a subscript n. Okay, and remember, this is rotation by, this refers to rotation by 180 degrees divided 180 by n degrees. Okay, so 180 degrees by n rotation is denoted by Cn. So if you have C2, it is a 90 degree rotation. If you have C3, it is a 60 degree rotation. In crystallographic notation, in Hermann-Mauguin notation, their rotations are just denoted by the letter n. And in case you have a mirror, okay, and rotation whose axis is perpendicular to the mirror, okay, then often the symbol m by n is used. Okay, rotation and a perpendicular mirror is often sorry, it's denoted by n by m. N by m. Okay, so this refers to a rotation and a perpendicular mirror. So this is a rotation plus perpendicular mirror. Okay, so that's about these proper rotations. Okay. Now additionally you have rotoreflections. Now these are not used in crystals, but in molecular notation these are denoted by Sn. Sn means rotation by 180 by n degrees followed by a reflection in a plane perpendicular to the rotation axis. So Sn, I will write it down, equal to, this corresponds to rotation by an angle of 180 divided by n degrees followed by reflection about a perpendicular plane. Okay. So Sn refers to this particular symmetry operations, and what should be noted is that Sn axis is relevant when the individual axis, when the individual operation of rotation or reflection is not a symmetry operation. So but Sn is a symmetry operation. So that is the interesting case. Okay. Now Sn in Hermann-Mauguin notation we don't really use this. Okay, so there is no symbol for it, but we use rotoreflections. roto inversions. Okay, this is a rotation followed by an inversion, and this is denoted by n bar. Okay, n with a bar on top refers to rotation followed by reflection about a mirror about a plane that is perpendicular to the rotation axis. Okay. So, these are the two common notations, okay, and these are notations for the symmetry operations. So, these are either notations for symmetry operations or for symmetry elements. So, you can say that a crystal has a three axis of rotation. Okay, so it has a threefold axis of rotation. So, or you could say that it has a 3 bar axis. Okay, so that means there is an axis where has a roto inversion axis. Okay, so it has a certain roto inversion axis. So, it is the individual operations that are described by these symbols. Okay, so I'll just write for completeness n bar equal to rotation by 180 degrees divided by n followed by inversion about the center of inversion. Okay, and we saw that in the case of a tetrahedron that sometimes that a tetrahedron has a C2 axis, but it has a 4 bar. So, it has a twofold axis of rotation, but it has a 4-fold inversion axis. Okay. So, sometimes these individual operations of rotation or inversion might not be a symmetry operation, but their combination happens to be a symmetry operation. Okay. So, I'll talk a little bit more about the Hermann-Mauguin convention. So, this is most commonly used in crystallography. So, we have already said this. Okay. And what is done is first we use it to define the various symmetry operations, and that we have already seen. Okay. So, we have things like n, m, n bar, okay, and so on, and we'll see soon that we can also use it to classify the symmetry operations that are not point symmetry operations. So those are the translational symmetry operations. Okay, and later on we will see that the same Hermann-Mauguin convention is actually used to classify the different crystals. Okay. So, you will see things like example you can have something like P6mm. Okay. So, this is a Hermann-Mauguin convention for a crystal. Okay. It's not a Hermann-Mauguin convention for a symmetry operation, but essentially each of these names we will see later that how to understand the meaning of how to interpret such a name. Okay. So, that convention is something that we will look. Okay. And I also already mentioned that if you have a rotation axis with a perpendicular mirror, okay, you use this symbol n by m. Actually it is m n divided by m. Okay. So, it is they should be written one below the other. Okay. So, for example, you can have something like a P 6 by m, you could have something like this in the notation for the crystal. Okay. So again we look at all these in more detail when we come to classification of crystals. Okay. But for now I want each of you to realize that this Hermann-Mauguin convention is actually extremely important, and that is what will be used extensively in classifying crystals and identifying the various symmetry operations in crystals. Okay. So, I will conclude this lecture here, and we will continue in the next lecture. Thank you.